Okay, today we will talk about a generator ventilation system, okay, as per the manufacturer. I will open one of the layout, okay, where okay, so this is the generator ventilation layout, okay, where you can see there is a generator inside, okay, and this is an enclosed space, right? Then you have a sound alternator, then we have a intake alternator, then you have a louver, okay, then you have a fans, okay. So this is the basic layout of the generator ventilation, right? I'll just start with the introduction part, okay. I think everyone know about the power transmission, right? Starting from generating power plant to the distribution plant, right? Say for example, whenever you say the generating station at the plant room, the power will pass through the transformer, okay, then it comes through the transmission line, then secondary transmission line, then through the power distribution, then it comes through the building through the transformer, okay. Normally it gives the power from the power station to our building, right? This is a transmission line, okay. So whenever the power pass through the transmission line, that produce a heat, because it is the power is flowing through the cables, right? Flowing through the bus bar or cables or whatever it is, okay. So whenever the current pass through the cables, it will produce a heat because it works, right? So it produces a lot of heat, okay. Similarly, whenever it pass through the transformer, it produces a lot of heat, right? Clear, right? Okay. So say for example, this is the authority power. Whenever you get the power from the generating plant, which comes from the authority, okay, through the transformer we are getting power, right? And also you have a generator. Say for example, this is the normal scenario, and also you have another scenario called backup, like power failure scenario, right? So that during that period you will get a power from the generator, right? The generator will give directly to your building, like a LV panel, right? Say for example, if I open the layout here in one of the project where you can see there is a transformer room, okay, then you can see that LV room, then you can see there is a generator room, right? Say for example, when you see the as per the layout, you can see there is a power coming from the power plant room through the transmission line. It comes to the LV room through the transformer, right? So normally before the transformer you have a HV plant room, okay, you can call it as a HV, high voltage room, and also you have a low voltage room, okay. So when you say high voltage room, it will be like 11 kV or 33 kVA, something like that, as a very high power, okay. So why the high power is, why they are converting into high voltage? Because you can reduce the cable size, okay. If you know the power equation, okay, when you increase the voltage, the current will reduce, right? When you increase the current, the voltage will reduce, okay. So to reduce the cable size, what they are doing, they are going to increase the voltage. So when you say 11,000 kilovolt, that means that much of voltage they are passing through the cable, right? So that means the current will be reducing, so that they can reduce the cable size, right? So that is why you have a high voltage up to your building, okay. Then after that you will convert from high voltage to the low voltage through the transformer. You will step down, say for example 1100 kV to 400 voltage, like what is required for the building, okay. So during this transmission, what will happen, the transformer will produce a lot of heat, okay. And also during the power failure, the authority power will cut off, and then the power will come from the generator, right? Okay, the generator will give the power to the LV, then LV will give the power to your building, like wherever you have SMDB, MDB or distribution DB, okay, and it will give the power to your lights, whatever the accessories like equipments, it will give the power from LV to the building, right? So you have a two source of power supply, one from the authority, one from the backup power, which is coming from generator, right? And both produce a lot of heat, okay. Say for example, if you talk about generator, you can keep it in case by case. Say for example, I have one case that where I have kept the generator at open place, right? That is without any enclosure, right? Okay, so when you keep it at the open place, you require, whenever the generator operates, okay, the generator will produce a lot of heat, that is one, and also the generator has to burn, right? There is a fuel, the generator has to burn, okay. So what will happen, it has to get some oxygen from outside, okay. So for the proper operation of generator, you need proper cooling from outside, and also ventilation, the amount of air required for combustion purpose. Clear, right? Okay, so you can keep the generator either in open position or you can keep it in the closed position, right? So you have a two type of generator. One is open generator and one is a closed generator, enclosed generator. Okay, there are two types. Okay, so if I go through the introduction part, let me open. So you can see this is the theoretical part for generator ventilation. Okay, so basically generator ventilation is crucial to ensure the safety, efficiency and longevity of the generator. Okay, so if the generator has to perform with the proper efficiency, you have to properly ventilate. Okay, the generator has to work without any excess heat. Okay, so proper ventilation helps in maintaining an optimal operating environment by preventing overheating and removing harmful gases like carbon monoxide and nitrogen oxide. Okay, so whenever, say for example, you have a generator which is in enclosed space, okay, it produces lot of heat. So that heat to be properly ventilated. So that is what it is given here. Proper ventilation helps in maintaining an optimal operating environment by preventing overheating. If the generator overheat, then the efficiency of the generator will be going down. It cannot give proper power supply. And also you have to remove harmful gases like carbon monoxide, nitrogen oxide. Clear, right? Okay, so basically what is required, you have to have a airflow and temperature control, right? So you have a inlet and exhaust vents. So you can say if you go through the layout, you have a inlet and exhaust vents basically. Okay, so you have to properly cool the generator by means of supplying proper ventilation, and also you have to provide proper air for the combustion purpose. Okay, so here you can see that inlet and exhaust will ensure that there is adequate air supply for combustion and also for cooling. Typically intake vents bring in fresh air while exhaust vents remove hot air. The inlet should allow enough air for both generator cooling system and combustion process. Clear, right? Is everyone clear for the basic concept?
Yes.
Yeah.
Okay, then the ambient temperature control. Maintain the room temperature within the recommended range for generator. Excessive heat can reduce generator efficiency and lifespan. Install fans or HVAC system if necessary to control the temperature. That is why we go with the exhaust fan or supply fan for the proper ventilation. Okay, then again the proper clearance. There should be enough space around the generator for air to circulate freely and avoid hot spots. Manufacturers usually specify the minimum clearance needed for the optimal airflow. Okay, so then you have an exhaust system like exhaust gas removal. Generators produce harmful exhaust gases such as carbon monoxide. Ensure the room has an exhaust system such duct or pipes to safely channel these gases outside. Say for example, if you go to the generator layout, you have an exhaust pipe, right? So whatever the combustion, the fuel will get burned, and after that it will become a fuel. It will become a flue gas, and the flue gas will be taken out through the fume exhaust pipe. Okay, then it will be discharged outside, right? Okay. Then you have a ventilation rate. So when you do the calculation for the ventilation rate, there are different methods. Either you can do based on the ACH method or based on the heat. Fan sizing ensure that fan or system or appropriately sized to handle the heat load of the generator. Okay, so when you go to the generator catalog, say for example, if you go to one of the catalog here, you will find what is the generator heat, total heat rejection which is required for the generator, how much heat produce the generator, right? So you have to have a proper heat rejection based on that particular heat which is generated by generator, right? Okay, then you require sound attenuator. Okay, say for example, you have a office area. Okay, inside that, near to the office area, you have a generator. When the generator, during the power failure scenario, if the generator runs, it will produce a lot of noise. Okay, so that will disturb your neighborhood, right? So you have to have a proper sound attenuation. Okay, then reduce redundancy and monitoring, like a backup ventilation fans if required. Okay, then there is a proper maintenance, regular inspection, filter replacement. Okay, then airflow design and requirement. Efficient airflow is essential for generator ventilation to prevent overheating, ensuring proper combustion and maintain the generator performance. So this is the basic theoretical part which I will share it with you. You can have a look, right? Okay, so basically exhaust gas ventilation, then cooling system integration, radiated cooling generator, safety consideration like a gas detection, ventilation fan, alarms, okay, fire protection, okay, noise control and attenuation, right. So when you calculate the ventilation rate calculation, there is a equations, okay. Airflow rate is nothing but heat rejection multiplied by 1000 divided by air density multiplied by specific heat of air multiplied by temperature rise. This is basically the same equation what we have calculated, Q equal mCp delta T, right.
The temperature rise is basically the delta T, right?
Yeah, delta T.
Okay.
Okay, so that we will see now. So this is the basically a theoretical part to understand what is required for the generator, right. Basically you have to have a air and temperature control, proper temperature control, right. Then you have a exhaust system, ventilation rate, sound attenuation, then you have a redundancy. You have sometime if you go to critical system, you have a backup ventilation and also backup generator also sometime may require. You have to have a proper inspection. Then the airflow design and requirement, right, for the inlet and exhaust, okay, for the proper cooling and for the proper combustion. Okay, so you have a different method to calculate exhaust ventilation float. Either you can calculate based on air change per hour method. There are different methods. Okay, then you can see exhaust gas ventilation for the proper routing, backup pressure consideration, exhaust stack placement. The whenever you have a fume gas, that should be properly kept it outside, okay, for the exhaust stack placement, okay, so that it will not be disturb any of your neighbors. The whatever the smokes, it will be discharged to the atmosphere directly, okay. So that is a proper exhaust stack placement, okay. Then muffler and sound attenuation for the sound attenuation purpose, okay. Then you have a cooling system, radiator cooled generators, okay. So whenever you have a properly when you design the layout, you have to have a proper, this is the radiator portion, okay. You have to properly direct the cooling air towards the radiator so that it can cool, right. Otherwise the generator will get heated up and it will become excess heat, which will reduce the efficiency of the generator, okay. Then you have to consider about gas detection, ventilation failure alarms like carbon monoxide, nitrogen, right. Say for example, if you see here there is a lot of fumes, so the fume is nothing but CO, right. So the fume has to be taken properly to the fume exhaust piping, okay. Then there is a fire protection, noise control, attenuation. Then there is a ventilation rate calculation methods. How to calculate ventilation rate, you can see here there is a formula. I think we have seen last time the equation called Q equal mCp delta T, right. So this is the Q, which is nothing but heat. M is nothing but mass flow rate. Mass flow rate is nothing but airflow multiplied by air specific heat, sorry, airflow rate multiplied by air density, right. Then Cp specific heat multiplied by delta T temperature rise. So this will give you the equation, right. So this is one of the method to calculate the airflow rate, okay. Say for example, you have a heat rejection kilowatt in kilowatt, okay. So that one, if you go to the standard catalog for one of the generator like Cummins, okay. So here if you go to the catalog, say for example here you have a model number, then what is the frequency, whether 50 hertz or 60 hertz, what is the type of fuel, diesel or whatever they are going to operate, right. Then you have a fuel consumption, okay. There is a fuel consumption is given here. Then also there is a type of generator. You have a 3 type of generator basically. There is a standby, prime, and you have a continuous generator, okay. The standby generator will operate only during the power failure scenario, okay. The prime generator can run for longer period but within limited hours per year, okay. The continuous generator can run for 24 hours for uncontinuous like unlimited hours. You can operate at any hours. So standby generator will be normally used for where there is a authority power failure is expected in very maybe minimal period. So then you can use standby generator, okay.
Like in residential buildings and all, we use standby generators, yeah.
Which one?
In residential buildings, what the projects what we have done with Iman.
Yeah.
Standby generators.
That is standby generator because the power failure will happen very rare, right.
Yes.
Okay.
Yes.
Where you will use prime generator, say for example you have office area like temporary offices in site, okay. So there where you don't have a power from authority, okay. So say for example you are going to operate 8 hours per day, so there you can use prime generators, okay, for longer period but lesser capacity. It will not give you 100% capacity. it will give you like a 70% or 80% capacity of the generator which is sized for, right? Okay. Now there is another one critical continuous operation, say for example like data centers or hospitals where you cannot expect like efficiency, like reduce in efficiency. So there you will use continuous operation generator, that is called like you can run for any hours, within unlimited hours you can run. So that is another type. Okay. So in this catalog, say for example if I am going for which type generator, whether 706 or 640, depends upon your calculation, you can select which type of generator you are going for. Okay. Then if I go further down, here it is given air combustion, how much air I have to give for combustion for the generator to operate. Okay. Here it is given 52.7 meter cube per minute, right? Okay. Then you can see that exhaust gas, right? For example, whatever the after the burning, okay, after fuel burned, how much gas expected, the temperature is around 507 temperature expected. Okay. And what is the gas flow? It will be around 129.9 meter cube per minute expected after burning, right? And then you can see that radiator cooling, how much, what is the heat will be generated. It is based on the catalog which is 21,610 BTU per minute heat.
Just one doubt.
Yeah.
This exhaust gas temperature at 507.
Yeah.
So this would be modulated before it gets out to the environment, or how is it?
No, it will be discharged at the same temperature, because there is no, you cannot reduce the temperature. It will be discharged at same temperature. That is what you can see the exhaust is stacked at very high level, right?
And insulated.
Yeah, and also insulated. Yes.
Insulated is the pipe.
Rock wool insulation. Yes, that is a that you are going to discharge through the pipes, right?
Yeah, to the pipes, but let's say
it is a exhaust gas. It is not a liquid or solid item. Okay, when it discharges to the atmosphere, it will reduce the temperature. The temperature will go down, right? Say for example, if you stand in front of the generator, exhaust stack pipe, you can see that lot of fumes which is ejecting outside the generator, right?
I mean the flue gas pipe, right?
The flue gas pipe.
Gas.
Okay, so but when it comes to the atmosphere, when it comes to the sky, like atmosphere, it can reduce the temperature. It will cool down. But if you see that outside, you can expect around 507 degrees Celsius. So that is what, whenever you design the fume pipe, you will provide with the rock wool insulation, right?
Right.
Okay, so there is no process of cooling. It will come outside, then after that it will discharge to the outside atmosphere, then after that it will cool down. Okay, so then here you can see that what is the amount of cooling flow required. Okay, so if you go to this particular equation, I have given here the airflow calculation, how to calculate the airflow rate based on the heat rejection. But if you go to the catalog, they also given the heat rejection, and also they given the how much of airflow is required. 14.5 meter cube per second airflow is required for to cool the radiator, right? Clear, right?
Right.
Okay, and you can
but
see.
This cooling here has any particular temperature requirements, or it's just atmospheric air only?
Which one? This one?
The cooling air.
Oh no, this is just atmospheric air.
Okay.
Okay, so if I go further to the guideline, okay, there is one chapter 28 from ASHRAE. You can see that for the power plants, chapter 28 based on ASHRAE, right? This chapter discusses HVAC system for industrial facilities that produce process heat. So whatever the generator, it produces the process heat, right? Because when it processing heat and power for electrical generating station and transmission facilities, right? This chapter will discuss about power plants. Okay, the power plant, this chapter discuss HVAC system for industrial facility that produce process heat and power for electric generating station and transmission facilities. Okay, so this chapter will be used for the generator application, right? Okay, so here we are going to control the temperature and humidity basically. Okay, when you go to the design criteria for fuel fire plant room, you can see for the generator. For the diesel generator, what is the ASHRAE temperature? Maximum temperature will be 0.4% and 99.6% of the design outdoor as per ASHRAE. If you go to ASHRAE guideline, you will get this temperature. of the outside. Okay, like say for example in UAE, like 46 degree or 47 degree, whatever is the temperature as per ASHRAE Meteor software, right?
Yeah.
If you go to this guideline, so here you can see that hottest month temperature, like for 0.4 percentage, right? So you will take consider like 43.3 and 23.6 degrees Celsius, dry bulb and wet bulb temperature. So that is what the standard says. Okay, then the maximum temperature can be design outdoor plus 6. So the delta T can be like 6 delta T, right? Okay, so that is what in the equation you have to see the temperature rise. How much temperature it can go maximum? It can go from 6 degree from the outdoor temperature. So what is outdoor temperature, which is 43.6. If I go here, what is outside temperature? 43.3 degrees Celsius. Okay.
So it should be 43.3 plus 6 degree.
Yeah, plus 6 degree. But normally in UAE, what we will do, we will take a 46 as a maximum temperature, then we will take plus 6 degrees Celsius.
Okay.
Right? So this is the maximum, this is the delta T basically. Okay. Then go to this equation, you can apply the delta T here, temperature rise, right? And you know the specific heat of the air, which is 1.2 joule per kilogram degree Celsius for dry air, right? Okay. Then the density of the air in kilogram per meter cube. Okay.
Density of the air, we can consider 1.2. No, how much is it?
1.225 kg per meter cube.
Okay. 1.225. Okay.
Okay. So this is the, if you apply in this equation, you can able to calculate the airflow rate, right? Which is required for cool the generator. Clear, right? Everyone clear?
Yes.
So what is the heat rejection is given in the catalog for the generator catalog, and air density we know, specific heat capacity we know, and what is the temperature rise we know, and so that we can able to calculate airflow rate.
Parani,
Yeah.
apart from the equipment heat generation, we also have the space-wise heat generation, right? Should we also include that?
No, this is actually basically it is an open room, right? See,
Yeah.
for example, if you go to this particular layout, okay. If you go to this layout, okay, you can see the plan
Yes.
diagram. Okay, in the plan you can see there is a generator here, kept it here,
Yes.
and this is open to atmosphere. Like this is open to atmosphere.
Mm.
Okay, and also this is also open to atmosphere. You can see there will be normally air will be flowing through this area.
Correct.
Okay, so both side is open to atmosphere, so there is no chance of heat will be inside.
Okay.
Okay,
Fine.
okay, but if you are going to keep it in the basement, say for example in the basement, which is enclosed space, and this will be louvered, then you can provide a fan coil unit for the normal operation. Like when the generator is off, you can provide like a fan coil unit for the cooling the room.
Okay.
Okay, when the generator operates, that heat will be negligible. The heat, the surrounding heat. Okay, because the generator will produce a lot of heat, so that should be cooled. When you do during the commissioning of the generator, when you stand nearby, you have a lot of noise and a lot of airflow pressure inside the generator room. Okay, when you stand inside, right?
Yes.
Okay, now we will go case by case. Okay, say for example, if I have say for example I have one desert project, right? So in the desert project I can keep the generator outside, directly outside, right? So if I keep it outside, that means whatever the cooling for the radiator, it will be taken from directly from outside, and also whatever the fuel required, whatever the air required for the combustion, it will take directly from outside, correct?
Yes.
Okay, so you don't need of any mechanical works, additional mechanical works.
Yeah.
Okay, so say for example in such a case that some other places where the generator cannot be kept outside, it's not allowed, so you have to keep it one inside enclosure room, right? So you are going to keep it enclosure the room. Say for example you are going to have a generator here, right? And then you have an intake, and then you have a discharge, right?
Correct.
So you will provide with the louver, you will provide with louver here, intake louver. Okay, and what is the pressure drop accepted? There will be inbuilt generator, radiator fan will be part of the generator. Okay, so that generator will suck the air from outside and it will discharge the air to the outside, right? Okay, so this inbuilt generator, what is the maximum capacity? If you go to the catalog, you can able to see here 14.5 liter meter cube per second at maximum of 2.7 mm H2O, okay, which is nothing but 127 Pascal. So that is the pressure drop. So if that pressure drop, whatever the pressure drop, say for example, you have a ducting, right? You have a louver. You have a louver having pressure drop. Okay, then you have a duct to have a pressure drop. Sound attenuator have a pressure drop, right? Then say for example, you have a louver here. There is a pressure drop. So you have to calculate all the pressure drop based on the airflow rate. Okay, so that pressure drop should not exceed more than 127 Pascal. Okay, if it does not exceed 127 Pascal, then you don't require any additional exhaust fans.
Okay.
Clear, right? What I'm saying, you getting my idea? Like you do, because there is an inbuilt generator fans, so that can suck the air from outside and it can discharge the air to the outside. So that capable of supply, capable of this much flow and this much pressure.
So basically, if the pressure drop is less than 14.5,
no, 12.7.
sorry, 127 Pascal.
Yeah.
There's no need of any additional
Additional exhaust fans, right?
exhaust fans. Otherwise, if it's more, then we need to accordingly provide the.
Yes. Okay. Now, say for example,
just one small doubt. Like a case study, if we are taking in, I remember in Act 1 Act 2 project when we worked, there was additional exhaust fan there.
Yeah, that I will come to you. Okay. Okay. Now, say for example, I told you that there is a external office area, like office area where you need a generator to be within the enclosed space. Okay. So within the enclosed space, if you keep what is the minimum requirement? You have to provide a louver here, right, for the intake. Okay, and for the discharge, you have to provide louver again, right? Okay. So you have to connect to the generator, because if you don't connect to the generator, then this exhaust gas will be going inside the generator room. So you have to provide a ducting, right? So here, how many accessories you have? You have an intake louver, you have a discharge louver, then you have a connection piece. So you have to calculate all the pressure drop, how much pressure drop. So that pressure drop should not exceed more than 127 Pascal. If it exceeds more than 127 Pascal, then you will add one exhaust fan here, right? Okay. Now another case, say for example, I have office area nearby, the generator will be running, but during the generator, when it runs, it will produce lot of noise, right? Okay. To control the noise, what you will provide, you will add alternator, right? So this alternator pressure drop, normally if you go with any manufacturer, it will be approximately 40 Pascal, 50 Pascal to say sometime it will go to 100 Pascal, right? So when you say 100 Pascal here, it is going more than 200 Pascal, right? Then you have a louver, here, then you have a connection piece. So the total pressure drop will be coming around 200 Pascal or 250 Pascal. So in that case, your generator inbuilt fan cannot take that particular pressure, that particular air, right? Then what will happen if you don't provide if you provide this much of alternator, if you provide this much of accessories, what will happen? The generator fan will perform with less efficiency. So if it perform with less efficiency, the heat of the generator will go up. So then the generator cannot perform properly, right? So that is why you provide additional exhaust fan to pump the air from outside to inside, so that this will have a less work. Clear, right, everyone?
Yes.
Yeah.
Okay, so that is why we provide additional fan. Okay, so when you do the calculation for the additional fan, so what is the requirement? One for the radiator cooling and one for the combustion, right? And what is the radiator cooling flow requirement? If you go to the catalog, it will be 14.5 meter cube per second, and for the combustion, 52.7 plus meter cube per minute. Okay, so that is the fan capacity basically. So if you go to the catalog, you can calculate directly by using this flow rate directly from the catalog.
Design should be based on 52.7 meter cube per minute plus 14.5 meter cube per second
Yeah.
and additional this
Yes,
thing.
I will show one of the project by previous projects, right? If you see this one, generator ventilation calculation, genset ventilation calculation. Okay, you have a as a sample calculation capacity 2000 kVA and the dimension engine airflow. So this engine airflow is nothing but for combustion purpose, which is 2.3 meter cube per second, right? And for the radiator airflow 30.2 meter cube per second. Okay, so here you can see number of unit will be 2. Okay, whatever the how many generator you can have. Okay, so what is the intake air sizing? You can see engine airflow plus radiator airflow, which is 30.2 plus 2.3. So this is the flow of the intake sizing, intake air sizing. If you have a 2 units, then your total airflow rate will be 65 meter cube per second. So the sand trap intake louver will be sized for 65 meter cube, right? When you see the exhaust airflow rate, okay, exhaust airflow rate.
Why does it say at 1 meter per second? Is the
No,
speed?
no, this is for the sand trap louver sizing.
I think the
Louver.
Okay.
Okay. Now, if we talk about exhaust air sizing, we have considered only radiator airflow, right?
Yes.
Because the engine airflow will burn, the fuel will burn that particular combustion air, then it will go through the flue gas pipe, right?
Yes.
So when you discharge, you have only radiator airflow. Clear, right? So this is the flow rate calculation. This is one of the method.
Okay.
Okay. The another method will be by using this equation. Airflow rate is equal to heat rejection divided by air density divided by specific heat divided by temperature rise.
All right.
Okay. Now, say for example, I have another case that there is a lot of noise is producing, right? So you have to have a alternator here. So when you add the alternator, the pressure drop will increase here. So that is why we are going with the external fans. Clear, right? Okay.
Yep.
Now there is a guideline here. There is an engine room ventilation guideline. Okay. You can see there is application and installation guide from one of the manufacturer. Engine room ventilation. So here also you can see the sizing consideration is based on cooling air and combustion airflow, right? Okay. So the ventilation airflow calculation will be based on the same what I have shown here. Calculating required airflow rate for engine room enclosure temperature. You have to maintain temperature, atmospheric heat rejection correction factor here. Okay. So when you go further down, there is a equation, same equation here. M equal to Q heat divided by density specific heat multiplied delta T plus combustion air, right? So here you can see the equation here. V equal to ventilating air, H is the heat radiation, density of the air, Cp specific heat, delta T. The same what I have shown here. Right? Okay, plus combustion air. Okay. Now there is a factor. So this factor is very important. Say for example, if you go further down, okay, you can see the picture here, right? So how you are going to discharge? You are going to discharge in front of the radiator. That is why if you see one of our layout where we designed in our project, we have discharge in front of the radiator, right? So that it can cool the radiator. Okay, so that is what you can see the guideline as well. You have to discharge the air at the inlet of the radiator, right? And you can take out from any direction. So when you go to this equation, you can see the factor will be 1, right? So whatever you are calculating the airflow rate, you can calculate based on 1 factor. Okay. Then ventilation type 2. So here another case. Say for example, you are having intake also near to the radiator, and you are going to taking out. So this also again factor 1. Okay. Now if you are calculating like this, say for example, you are discharged at very high level, right? And exhaust at high level. Then what you have to do? You have to multiply by 1.5 times. Whatever you are calculating airflow rate, you have to calculate 1.5 times. So which is very simple.
Any reason?
Yeah.
Any reason to increase the 50% more?
Because you are not supplying directly to the radiator. So the radiator will get overheat.
Okay.
So that is why you are supplying more air.
More air. Okay.
Clear, right? Now you have another case. So here see, this radiator is here, and you are going to supply here on the top of the generator. So this is the airflow rate. This is the airflow path. This is the airflow path. So that means the generator is not getting proper cooled radiator. So you have to have a 2.5 times of the calculated airflow rate.
Fine.
Okay, and then another case. Say for example, if you are going
No,
to keep it,
I didn't get that point. Can you please that one point I didn't get.
see, say for example, normally this is a radiator, right? So this has to be cooled properly, right? Okay, so that is what
Right.
you are going to calculate the heat dissipation. Then we are going to calculate the airflow rate, how much airflow rate is required. But the airflow should be directly on near to the radiator, so that it can properly cool, right?
Right.
Okay. Suppose if your air outlet is somewhere away from the radiator, what will happen? The air will not get the radiator will not get proper airflow, right? So that is why you are going to add like the correction factor, like one times, 1.5 times, 2.5 times.
Okay, noted.
Okay. So here you can see the inlet is very far away from the radiator. So that is why you have a 2.5 times. You have to multiply it so that the radiator can be cooled properly, right? Okay.
Noted. Okay.
See, for example, if you see like this is the intake louver and this is the exhaust louver. So that means the radiator, the air is not properly cooled. The radiator is not properly cooled, right? So the generator will be overheated. So this is the incorrect airflow. So whenever you design, you should not design like this. Is it clear?
Yes.
Okay, so this is one of the sample layout in our previous projects, where you can see there is a enclosed space, right? There is a radiator, generator. Okay, this is the fume exhaust will be properly taken out to the atmosphere. Okay, you can see the layout here, piping layout. It will be taken outside to the atmosphere for the fume exhaust, and for the intake you have a louver, and you have a discharge. You have a louver here. To control the noise, we add the alternator. Right? Okay, and when you add the alternator, the pressure drop goes high, more than to 127 Pascal. So we have to add the exhaust fan, and the sizing of the exhaust fan will be engine airflow rate plus radiator airflow rate. So this is my intake air sizing. So that means this is my intake airflow rate for the fan. So this is one of the method. If I have a heat dissipation, then I can calculate by using this method, right? Okay, this method. So I can calculate the flow rate for the intake, right? And also for the discharge through the radiator. Okay, in case assume that I have my discharge at very high level. Say for example, I have to discharge at the roof. So that means the static pressure also will increase here. So that means I have to add one exhaust fan. Same like supply fan, I have to add one exhaust fan to discharge outside, right? So that depends upon the project. Okay, to calculate the discharge fan will be based on the radiator airflow rate, and when I size my supply airflow rate, I will be sized based on engine airflow plus radiator airflow, right? If I keep my intake near to the radiator, my correction factor will be 1. If I keep it away, like on the top somewhere here or somewhere in different on the top of that, then I have to add the correction factor maybe 1.5 or 2.5%, right?
But how will you determine the correction factor?
No,
Based on
depends
what
upon your
data?
inlet. Say for example, I am going to depends upon my layout arrangement. Assume that I cannot keep it here, maybe something is there. So what I will do, I will going to keep it, run the duct like this, and I will run the duct like this, for example, on the top of the generator. So then I have to add 2.5 times. Okay, assume that I cannot keep my generator alternator somewhere here. I have to keep it like this because there is something here. So here then I will add 1.5 times, right?
Okay.
So how to calculate the airflow rate, everything you have good idea, right? Okay.
Yes.
I will be sharing this particular I'll be sharing this generator ventilation theoretical part where you can go through, right?
All right.
Okay.
Right, noted.
Yeah. Next one we have a transformer ventilation, but we will discuss next class. it takes same time, like 1 hour it will take. Okay, so I will be
Okay.
sharing the generator ventilation documents. Just to go through the document, get some idea how the generator ventilation is calculated.
Noted.
Clear, right? Yeah.
All right.
Thanks everyone.
Thank you, Palin.
Yeah, thanks.
Thank you so much.